A rare visitor from deep space is racing through our solar system at unprecedented speed, and NASA's latest data has left scientists questioning everything they thought they knew about cosmic visitors. 3I Atlas, the third confirmed interstellar object ever detected, exhibits characteristics so unusual that some researchers are considering the unthinkable. Could this ancient wanderer be more than just a natural comet? As we uncover its secrets, the implications for humanity's understanding of our place in the universe become increasingly profound and, honestly, pretty terrifying. The breaking discovery. On July 1, 2025, the NASA-funded Atlas Asteroid Terrestrial Impact Last Alert System Survey Telescope in Rio Hurtado, Chile, first detected an unusual object later confirmed as 3I Atlas. This interstellar comet was initially spotted at a distance of over 4.5 astronomical units from the Sun, activating alarms across the global astronomical community. Its detection marked the third confirmed interstellar object ever observed passing through our solar system, following 1I Oumuamua in 2017 and 2I Borisov in 2019. The initial observations revealed a hyperbolic trajectory with an incredibly high orbital eccentricity of 6.141, the highest ever recorded for any known interstellar visitor. Larry Deneau from the University of Hawaii's Institute for Astronomy immediately recognized that this wasn't an ordinary solar system object, but a rare visitor that had been journeying through space for billions of years. The object's incoming velocity of 58 kilometers per second relative to the Sun marked it as the fastest interstellar object ever detected, surpassing both Oumuamua and Borisov by significant margins. From the outset, astronomers recognized that 3I Atlas was fundamentally different, initiating a worldwide mobilization of observatories dedicated to tracking this cosmic traveler and unraveling its profound mysteries. The discovery story. Between June 25 and June 29, 2025, the Atlas system had been gathering precursor observations that would later prove crucial in understanding 3I Atlas's trajectory and properties. These pre-discovery images, retrieved from survey archives and including work by the Zwicky Transient Facility at Palomar Observatory in California, helped confirm the object's interstellar path. Sam Dean, an amateur astronomer, contributed critical early tracking data, noting that the comet's trajectory through dense star fields near Sagittarius made early detection extremely difficult. The object's path passed through crowded cosmic neighborhoods, where countless background stars created a celestial camouflage, explaining why it had escaped discovery earlier despite being in the inner solar system for weeks. John Tonry, principal investigator of the Atlas project, immediately coordinated with facilities across the globe to confirm the object's characteristics once it was detected. The challenge of identifying 3I Atlas stemmed from its approach through regions where most sky surveys don't venture due to the overwhelming stellar background. This cosmic game of hide-and-seek had been ongoing since June 14, 2025, when the earliest pre-discovery images show the object silently crossing space. The rapid coordination between professional and amateur astronomers from multiple continents underscores the unprecedented global effort invested in monitoring this mysterious visitor. A stranger in our midst. 3I Atlas exhibits characteristics so unusual they continue to baffle the scientific community and challenge our understanding of natural cosmic objects. Traveling at a staggering 61 kilometers per second relative to the Sun, it far exceeds the speeds of its predecessors like Oumuamua and Borisov, making it the fastest interstellar visitor ever recorded. Its brightness is particularly notable, with a distinct coma and tail forming as solar radiation heats its surface, causing ice sublimation that creates spectacular visual displays. David Jewett from the University of California, Los Angeles, noted that the comet's tail and dust emissions provide rare data about materials formed in distant star systems billions of years ago. Perhaps most puzzling is that its trajectory lies almost perfectly within the ecliptic plane, the flat disk where most planets orbit the Sun, an alignment with merely a 0.2% probability of occurring by random chance. This mathematical precision has prompted serious speculation about whether the object's path represents natural celestial mechanics or something far more intentional. The combination of unprecedented speed, unusual brightness, and statistically improbable orbital characteristics raises fundamental questions about whether 3I Atlas is truly a natural object, or represents something far more enigmatic that challenges our basic assumptions about interstellar visitors. the predecessors. So, to really understand the true significance of 3I Atlas, we have to take a look back at the two remarkable interstellar visitors that came before it, each bringing their own, well, unsolved mysteries. The first, 1I, Oumuamua, was discovered in October 2017 by astronomer Robert Warwick at the University of Hawaii. It immediately stunned the scientific community with its elongated cigar-like shape and honestly, its completely unexplained acceleration away from the sun, all without any visible signs of outgassing. This mysterious acceleration just defied conventional physics and sparked some pretty intense debate about whether the object could be natural or possibly artificial. Then, in August 2019, amateur astronomer Gennady Borisov discovered 2I Borisov from his observatory in Crimea. This one proved to be a more traditional active comet, showing the typical outgassing behavior you'd expect from solar system visitors. The stark differences between these two ancient travelers, one mysterious and possibly artificial, the other conventionally comet-like, have really intrigued astronomers worldwide and, more importantly, set important baselines for comparison. Mark Norris from the University of Central Lancashire has pointed out that 3I Atlas, being the largest and brightest interstellar object yet discovered, gives us unprecedented opportunities to compare and contrast with its predecessors. This growing catalog of interstellar visitors is finally starting to reveal patterns that could unlock secrets about the diversity, origin, and true nature of these cosmic wanderers from distant star systems. The cosmic journey. 3. I-Atlas's trajectory through our solar system, honestly, follows a carefully orchestrated path that gives us optimal opportunities for comprehensive planetary observation. The object will reach perihelion on October 29, 2025, getting close to the Sun at about 1.36 astronomical units, positioned just perfectly between the orbits of Earth and Mars for extended observation. At perihelion, it'll hit maximum speeds of nearly 68 kilometers per second, which really shows off the extreme velocities you get with interstellar travelers. Paul Chodas from NASA's Center for Near-Earth Object Studies has calculated that while the comet poses no threat to Earth, keeping a safe distance of at least 1.8 astronomical units, its path brings it remarkably close to Mars, Venus and Jupiter during its trip through the solar system. The precision of this trajectory is pretty striking. It allows close approaches to 3 major planets and provides optimal vantage points for studying inner solar system dynamics. Karen Meach from the University of Hawaii emphasizes that this close approach sequence is, honestly, an unprecedented opportunity to see how an interstellar object interacts with different solar environments and planetary gravitational fields. The object will pass just 0.19 astronomical units from Mars on October 3rd, followed by a 0.65 AU approach to Venus on November 3rd, creating a sort of reconnaissance pattern that seems almost deliberately designed for a comprehensive solar system survey, rather than just a random cosmic passage. A scientific goldmine. 3I Atlas, really represents an unprecedented scientific treasure trove for astronomers and planetary scientists who are studying materials from beyond our solar system. With an estimated diameter somewhere between 0.32 and 5.6 kilometers, it's significantly larger than previous interstellar visitors. That means it actually allows for detailed study of its composition, structure, and evolutionary changes as it interacts with solar radiation. The Hubble Space Telescope, operated by teams led by David Jewett at UCLA, has been tracking dust emissions and nuclear activity, revealing ongoing sublimation of ancient ices and continuous dust release from the object's surface. These observations are providing crucial insights into the comet's volatile content and primordial materials, likely preserved for over 7 billion years, predating our entire solar system's formation. Stephanie Malam from NASA Goddard Space Flight Center is coordinating advanced spectroscopic observations using the James Webb Space Telescope to, hopefully, identify complex organic molecules and unusual isotopic signatures that could reveal the object's stellar birthplace. Current analysis has already confirmed the presence of water ice, both as solid grains and vapor, along with hydroxide ions, suggesting a water-rich composition that's typical of objects formed in the outer regions of planetary systems. The ongoing research aims to characterize the complete molecular makeup, including potential carbon monoxide, methane, and complex organic compounds, offering rare glimpses into the chemical building blocks and formation processes of distant star systems. Unanswered questions. Despite intensive global observation campaigns, 3I/Atlas continues to harbor profound mysteries that challenge our fundamental understanding of interstellar objects and their origins. The object's precise nuclear size remains frustratingly uncertain because the surrounding active coma obscures direct measurements of the solid nucleus, which complicates crucial density and mass calculations needed to determine its true composition and internal structure. While spectroscopic analysis has confirmed the presence of water ice and organic compounds, the detection of other expected volatiles like carbon dioxide and carbon monoxide remains elusive, raising questions about the object's formation environment and preservation mechanisms during its multi-billion-year journey through space. Julia de Leon from Spain's Instituto de Astrofísica de Canarias emphasizes that the object's unusual thermal properties and outgassing patterns don't conform to standard cometary models, suggesting either exotic compositions or structural characteristics not found in typical solar system objects. Perhaps most puzzling is the object's remarkable preservation state. How materials billions of years older than our solar system could remain so well preserved and chemically active after eons of exposure to cosmic radiation and interstellar conditions. Some researchers are beginning to debate whether the object represents a completely natural phenomenon or exhibits features that might indicate artificial construction or enhancement, a possibility that would fundamentally challenge our understanding of what's possible in the cosmos. The alien question. The possibility that 3I Atlas represents humanity's first encounter with extraterrestrial technology has, sparked some pretty intense scientific debate and forced researchers to confront some uncomfortable questions about the object's true nature. Avi Loeb, who's Harvard's Frank B. Baird Jr. Professor of Science, has really emerged as the most prominent advocate for seriously investigating artificial origins. He cites the object's statistically improbable trajectory, its unprecedented velocity, and honestly, its unusual structural characteristics as evidence that, warrant extraordinary investigation. Loeb's analysis suggests that the mathematical precision required for 3I Atlas's path, which actually provides optimal reconnaissance opportunities while passing close to multiple planets, exceeds what we'd reasonably expect from random cosmic events. His Galileo project at Harvard has been mobilized to conduct systematic observations using multiple telescopes worldwide, specifically searching for signs of artificial construction or technological signatures. However, mainstream astronomers like Sarah Seeger from MIT and Alan Fitzsimmons from Queen's University Belfast urge extreme caution, emphasizing that extraordinary claims require extraordinary evidence and that natural explanations should be exhausted before considering artificial hypotheses. The scientific community now finds itself balancing healthy skepticism with the recognition that, if 3I Atlas does represent extraterrestrial technology, the implications for humanity's understanding of our place in the universe would be, revolutionary, and potentially terrifying in their scope and consequences. Observing the visitor. Astronomers across the globe have mobilized an unprecedented array of telescopes and instruments to study 3I Atlas as it journeys through our solar system, creating the most comprehensive interstellar object observation campaign in history. Major facilities including the Very Large Telescope in Chile, NASA's Hubble Space Telescope, and the revolutionary James Webb Space Telescope are collaborating to collect multi-wavelength data that could, hopefully, unlock the secrets of this cosmic visitor. Michelle Bannister from the University of Canterbury notes that this coordinated effort involves over 50 professional observatories and, honestly, numerous amateur astronomers contributing observations and analysis. The Southern Astrophysical Research Telescope has been conducting detailed spectroscopic analysis to identify specific molecules and compounds in the object's coma and tail. Ground-based facilities like the Gemini Observatory and Keck Observatory in Hawaii are providing continuous monitoring of brightness changes, rotational periods, and thermal emissions that reveal internal heat distribution patterns. Canada, France, Hawaii telescope observations have captured deep images showing faint cometary activity even at great distances from the Sun. This international collaboration represents a new model for rapid response astronomy, with data-sharing protocols that allow real-time analysis and immediate follow-up observations when unusual phenomena are detected, ensuring that no critical information about this rare interstellar visitor is lost. Dawn of a new era. The detection and intensive study of 3I Atlas heralds the dawn of a revolutionary new era in astronomy, where interstellar objects transform from rare curiosities into, critical scientific targets that could reshape our understanding of galactic evolution and cosmic chemistry. Robert Jedica from the University of Hawaii estimates that technological advances, particularly the upcoming full operation of the Vera Rubin Observatory with its revolutionary LSST camera, promise to dramatically increase detection rates, potentially allowing astronomers to study dozens of interstellar visitors annually within the next decade. This technological revolution will create an unprecedented catalog of interstellar objects, providing statistical samples large enough to offer meaningful insights into galactic dynamics, planetary system formation processes, and the distribution of complex organic molecules across different stellar environments throughout our galaxy. Mark Norris from the University of Central Lancashire predicts that this growing database will reveal patterns in interstellar object populations that could answer fundamental questions about stellar evolution, planetary ejection mechanisms, and the chemical evolution of the Milky Way. As astronomers continue to unravel the mysteries of 3I Atlas and prepare for an influx of future interstellar discoveries, humanity stands at the threshold of a new cosmic perspective, one that will fundamentally transform our understanding of our place in the universe and the evolutionary history of our galactic neighborhood, potentially revealing whether we truly are alone or part of a larger community of cosmic civilizations. As 3I Atlas continues its mysterious journey through our solar system, it carries with it questions that could fundamentally alter humanity's understanding of our cosmic neighborhood. Whether this ancient wanderer represents exotic natural phenomena or, something far more extraordinary, the implications are honestly staggering. The coming months will be crucial as this interstellar visitor approaches its closest encounter with our sun, potentially revealing secrets that have traveled billions of years to reach us. Keep following InnoVision Tech for the latest updates on this developing cosmic mystery. Like, share, and subscribe. What if the Big Bang wasn't the beginning but a rebirth? What if our entire 93 billion light-year observable universe is just a single object inside a much larger, older cosmos? This isn't science fiction, it's a possibility being explored by theoretical physicists, challenging our most fundamental understanding of existence. The clues might be hidden in plain sight, in the behavior of black holes and the baffling arrangement of the most distant galaxies spotted by the James Webb Space Telescope. Let's explore this mind-bending possibility together. The standard Big Bang model. So, how did we arrive at our current picture of the universe? The story most of us know is the standard model of cosmology, first mathematically conceptualized by the Belgian priest and physicist Georges Lemaitre in 1927. It states that our universe exploded into being 13.8 billion years ago from a point of extreme density. From this intensely hot state, space itself began to expand. Over billions of years, gravity sculpted this expanding cosmos, pulling matter together to form the vast web-like structure of galaxies we observe today. This model is incredibly successful. It explains the faint afterglow of the Big Bang, the cosmic microwave background, and it accounts for the accelerating expansion of the universe. This acceleration, confirmed in 1998, is often attributed to dark energy, which makes up about 68% of the universe. When combined with dark matter, at around 27%, it appears 95% of our cosmos is made of stuff we can't see or understand. This means that all the stars, planets, and galaxies we can observe make up a mere 5% of reality. The singularity itself represents a point where our laws of physics break down, which is deeply unsatisfying for physicists. The model also struggles to explain why the universe appears so uniform in temperature over vast distances, a puzzle known as the horizon problem. Furthermore, the geometry of space is remarkably flat, an initial condition that seems incredibly fine-tuned and lacks a complete explanation. The black hole universe theory. What if there's a more elegant explanation, one that doesn't require inventing new particles or mysterious forces? A radical alternative, championed by physicist Nikodem Poplawski, proposes that our universe was born inside a black hole within a much larger parent universe. This idea flips our perspective on cosmic origins entirely. Instead of a singularity appearing from nothing, the theory suggests a physical process, the gravitational collapse of matter in a parent universe. Think of it like a star many times the mass of our sun collapsing to form a black hole, but on a cosmic scale. In this model, what we perceive as the Big Bang was actually the moment our universe formed inside that parent black hole. This framework elegantly resolves the issue of what came before the Big Bang, as the parent universe provides a clear preceding state. This cyclical model redefines our cosmic address, demoting our entire universe from everything that is to just one bubble in a potentially infinite cosmic foam. It also provides a physical source for the energy and matter in our universe, sourcing it directly from a pre-existing parent cosmos. In essence, the matter that makes up you, me, and the stars didn't appear from nothing, but was recycled from a previous cosmic iteration. Quantum mechanics and degeneracy pressure. Here's where things get really interesting, and it hinges on a core principle of quantum mechanics. Have you ever wondered what stops a dead star from collapsing forever? The answer lies in a rule established by the brilliant Austrian physicist Wolfgang Pauli. His exclusion principle states that identical particles like electrons cannot occupy the exact same quantum state at the same time. When gravity tries to crush matter into an incredibly small space, this principle creates a powerful outward push known as degeneracy pressure. The more you squeeze, the harder the particles push back. This is the force that supports white dwarfs against collapse, where matter is packed to a density of over 1 million kilograms per cubic centimeter. In even more extreme objects like neutron stars, the pressure is even greater, holding up against densities of over 100 trillion kilograms per cubic centimeter. This pressure is fundamentally different from thermal pressure, which supports a star like our Sun, as it doesn't depend on temperature at all. The strength of this pressure is truly staggering. It's the only known force capable of halting the complete gravitational collapse of a star's core. While we observe it in stellar remnants, applying it to a collapsing universe is a theoretical leap, but one grounded in established quantum principles. The crucial assumption is that these quantum rules hold true even at the unimaginable energies and densities of a universal collapse, providing a physical barrier against infinity. The bounce mechanism. So, if a universe collapses, what happens when this quantum pressure kicks in? Instead of crushing down to an infinite point, a singularity where physics breaks down, the collapse could halt and rebound. This is the Big Bounce, a concept heavily explored in loop quantum cosmology by physicists like Martin Bojewald. In this scenario, as the matter of a parent universe collapses, it approaches the theoretical maximum density allowed by physics, known as the Planck density, which is about 5.1 times 10 to the 96th kilograms per cubic meter. At this point, quantum gravity effects become so powerful they overwhelm everything else. This force stops the collapse in its tracks and triggers a massive explosive rebound. This rebound event would be incredibly brief but unfathomably violent, essentially resetting the cosmic clock for the new universe. To any observer inside this newly expanding region, that rebound would look and feel exactly like a Big Bang, while potentially preserving information from the prior cosmic cycle. This bounce also offers a potential solution to the black hole information loss paradox, a major conflict between general relativity and quantum mechanics. The paradox questions what happens to the information about matter that falls into a black hole if the black hole evaporates. A bounce mechanism suggests this information isn't destroyed, but is instead carried through the rebound event into the new universe, preserving the fundamental laws of physics. Evidence from early galaxies. This might all sound like fascinating speculation, but where's the evidence? It might be hiding in the deepest images of our universe, captured by the James Webb Space Telescope. According to the Standard Model, galaxies should build up gradually. Yet, JWST is finding galaxies that are bafflingly massive and mature. For instance, the GLASS JWST Early Release Science Program, involving astronomers like Rohan Naidu, has identified galaxies like GLASS Z12 at a redshift of 12, meaning we see them as they were just 350 million years after the Big Bang. These galaxies are already 1 billion times the mass of our Sun, far larger than our models predicted was possible so early on. Furthermore, these ancient galaxies appear to host supermassive black holes that are millions of times the Sun's mass, a phenomenon that standard models struggle to explain so soon after the Big Bang. Under the Standard Model, the universe's gas simply wouldn't have had enough time to cool and condense to form such massive structures so quickly. It's like finding a fully grown ancient oak tree in a field that was barren just a week ago. The timeline doesn't add up. These pre-existing black hole seeds would essentially give galaxy formation a massive head start, neatly explaining the presence of these cosmic anomalies. Galaxy rotation mystery. Now for another cosmic puzzle that might point to the same conclusion. In a random and uniform universe, you would expect galaxies to be spinning in all different directions, with a roughly 50-50 split between clockwise and counterclockwise rotations. But that's not what we see. A 2020 study analyzing over 200,000 spiral galaxies, led by computational astronomer Lior Shamir, found a significant imbalance. There appears to be a preferred direction of spin, and alignment across vast stretches of the cosmos. The statistical probability of this asymmetry happening by chance is less than 1 in a billion. This unexpected alignment, observed across a scale of billions of light-years, implies that processes during the formation of the universe were not as random as we thought. This large-scale pattern challenges the long-held assumption that the universe is the same in all directions, a principle that underpins virtually all of our cosmological calculations. This isn't a small, localized effect. The pattern of this cosmic spin is coherent across billions of light-years. Shamir's analysis shows the distribution of spin directions fits a dipolar pattern, meaning it has a distinct north and south pole just like a spinning magnet or planet. Such a large-scale coherent structure is extremely difficult to generate after the Big Bang and points instead to a fundamental property imprinted on the universe at its very creation. Schwarzschild cosmology. So, this idea of a universe inside a black hole isn't entirely new. It actually falls under a concept known as Schwarzschild cosmology. The name comes from Carl Schwarzschild, who, way back in 1916, found the first exact solution to Einstein's field equations describing the space-time around a spherical mass, what we now call a black hole. The model suggests that the observable universe is the interior of a black hole existing within a larger parent universe. From our perspective, the Big Bang was the formation of this black hole. From the outside, our entire cosmos would just look like a regular black hole. The size of this black hole's event horizon is defined by the Schwarzschild radius, and for a universe with the mass of ours, this radius is remarkably close to the radius of our observable universe. Mathematically, the singularity at the beginning of our universe is similar to the singularity at the center of a Schwarzschild black hole. The edge of our observable universe, a sphere with a diameter of 93 billion light-years, acts much like a black hole's event horizon, a boundary from which light cannot escape to an outside observer. From the outside, in the parent universe, our cosmic time would appear to be frozen at the event horizon, a classic effect of gravitational time dilation. Conversely, from our perspective inside, time flows normally, and it's the parent universe that is inaccessible to us. This fascinating duality means that our vast, dynamic cosmos could appear as a static, timeless object to any potential observer in the universe that spawned it. Black holes as universe creators. Let's take this idea to its logical conclusion. If our universe was born inside a black hole, what does that imply about the estimated 100 million stellar mass black holes in our own galaxy? It suggests that each and every one could be a gateway, a seed for a new baby universe. This paints a picture of a vast cosmic ecosystem, a multiverse where universes are constantly being born. This concept, known as cosmic natural selection and explored by physicist Lee Smolin, could even offer an explanation for the fine-tuning problem, the mystery of why the fundamental constants of physics are so perfectly set for life. If universes are constantly being created, then perhaps only those whose physical laws allow for the creation of stable black holes can themselves reproduce, leading to a multiverse dominated by life-friendly universes. This theory proposes that our universe is so adept at creating black holes precisely because it was born from one, continuing an unending cosmic lineage. Smolin's theory suggests that the physical constants, like the strength of gravity or the mass of an electron, could slightly mutate with each new universe born from a bounce. Universes with constants that are better at producing black holes will have more offspring, and over countless generations these properties will become dominant. This makes the fine-tuning of our universe for life not a lucky accident but a predictable outcome of cosmic evolution on an unimaginable scale. Torsion and space-time twisting. For a universe to bounce instead of collapsing into a singularity, you need a powerful repulsive force at extreme densities. One candidate for this force comes from an extension of general relativity known as Einstein-Cartan theory. The mathematics behind this were developed in the 1920s by the brilliant French mathematician Élie Cartan. This theory incorporates a property of spacetime called torsion, which accounts for the intrinsic spin of fundamental particles. This spin is a fundamental quantum property like mass or charge that gives particles an inherent angular momentum. In standard general relativity, spacetime can bend but it cannot twist, making the inclusion of torsion a significant modification needed for this theory to work. According to physicists like Nikodem Poplawski, at the densities found inside a black hole, the interaction between torsion and the spin of particles would create a powerful repulsive force. This torsion-induced bounce would be the mechanism that creates a new universe inside every black hole, making them not just cosmic destroyers, but creators. In Einstein's general relativity, gravity is described as the curvature of spacetime, like a heavy ball on a rubber sheet. Torsion adds another geometric property, a twist or spin to the fabric of spacetime itself, which only becomes significant at extreme densities. This twisting effect would act as a repulsive force, preventing matter from collapsing into an infinitely small point, and instead causing it to rebound outwards with tremendous force. Cosmic anisotropy. The evidence for a preferred direction in galaxy spins points to a concept called cosmic anisotropy, the idea that the universe is not the same in all directions. This directly challenges the cosmological principle, a foundational assumption in modern cosmology. This isn't just about galaxy spins. Anomalies in the cosmic microwave background radiation, first noted in data from the WMAP satellite and later confirmed by the Planck satellite, also suggest a large-scale alignment. Physicist João Magueijo famously dubbed this the axis of evil because it aligned with our solar system's plane, a result so strange it had to be a mistake, except it kept showing up with a statistical probability of being random at less than 0.1%. These anomalies, once dismissed as statistical flukes or errors in measurement, are now forcing a re-evaluation of fundamental assumptions, which is exactly how science progresses. The cosmological principle of isotropy has been a cornerstone of cosmology for nearly a century, so challenging it is met with significant scientific skepticism. However, as observational data from projects like the Sloan Digital Sky Survey and the Planck satellite becomes more precise, these persistent anomalies are becoming harder to ignore. If the universe truly does have a preferred direction, it would force us to rewrite our most basic models, and would strongly imply an origin story that involves rotation, just as the black hole universe theory predicts. From the impossible galaxies seen by JWST to the mysterious alignment of galactic spins, we are faced with observations that don't quite fit our standard story of the cosmos. The idea that our universe is inside a black hole born from a cosmic bounce offers a potential framework to explain these anomalies without inventing new physics. It suggests we might be part of an endless cycle of creation. What do you think? Are we living inside a black hole? Let me know your thoughts in the comments below. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching InnoVision Tech. What if the third interstellar visitor ever discovered was not a comet, but a billion-year-old alien messenger? In the summer of 2025, a faint object designated 3I Atlas streaked into our solar system, and a controversial hypothesis immediately captured the world's attention. This was no ordinary rock. The idea of advanced alien technology made global headlines, but NASA quickly stepped in with a powerful, evidence-based response that settled the debate. So what did they find? Let's explore this together. The Atlas discovery in Chile. So, where does a story like this begin? It starts with our ever-watchful eyes on the sky. The story began on July 1, 2025, when the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a robotic survey telescope at the El Sos Observatory in Chile, detected a faint object with an initial apparent magnitude of plus 19.5. To put that in perspective, that's about 250,000 times fainter than what the human eye can see. When astronomers calculated its orbit, they saw something remarkable. Its path was hyperbolic with an orbital eccentricity calculated to be a staggering 1.8. In astronomy, any orbit with an eccentricity greater than 1 is unbound. This number confirmed it was moving at approximately 55 kilometers per second relative to the Sun, far too fast to be a member of our solar system. Astronomers quickly named it 3I Atlas. Initial estimates suggested it could be massive, between a few hundred meters and several kilometers across, making it potentially much larger than the previous two interstellar visitors. The discovery was a major success for the Atlas network, which also includes telescopes in Hawaii and South Africa, proving its effectiveness in spotting these rare cosmic travelers. The detection of a third such object in less than a decade confirmed that these visitors are more common than previously thought, officially opening a new frontier in astronomy. Avi Loeb's controversial hypothesis. Here's where the story takes a sharp turn into speculative territory, thanks to a bold proposal from Harvard astronomer Avi Loeb. While most scientists saw a fascinating natural object, Loeb, known for his controversial work on Oumuamua, offered a different interpretation. In a scientific paper posted to the ArcSiv preprint server, Loeb pointed to the object's early lack of a visible coma and its trajectory. He suggested that if the comet continued to show no outgassing, or if its path deviated from a purely gravitational path without a visible tail to explain the push, it could be evidence of something artificial. He even raised the hypothetical possibility of malign intent, though he stressed this was an intellectual exercise meant to keep science open to radical possibilities. His argument, similar to the one he made for Oumuamua, hinged on the idea that any non-gravitational acceleration without a visible coma required a novel explanation. He proposed that a solar sail, a thin, lightweight craft pushed by the pressure of sunlight itself, was one such possibility that science should not be afraid to consider, however unlikely it might seem at first. The physics of radiation pressure are well understood, but for it to be effective, an object must have a huge surface area and an extremely low mass, characteristics not found in natural bodies. Media sensation versus scientific method. You can imagine what happened next. The words alien technology from a prominent Harvard astronomer ignited a media firestorm. The idea was captivating, offering a sensational explanation for a new cosmic puzzle. But this is where the rapid world of headlines collides with the methodical, patient pace of science. The scientific method isn't about finding the most exciting answer, it's about finding the one that best fits all the evidence. The broader astronomical community, while not dismissing Loeb's right to speculate, emphasized the need for patience and adherence to Occam's razor, the principle that the simplest explanation is often the best. Their stance was clear. We must first rule out all known natural phenomena before jumping to an extraordinary conclusion. The use of preprint servers like ArcSiv allows for rapid dissemination of ideas, but also bypasses the traditional peer review process, meaning speculative ideas can reach the public before they are fully vetted by other experts. Ultimately, the scientific consensus held that declaring an object alien required the elimination of every single possible natural explanation first, a very high bar that had not yet been met. NASA's comprehensive investigation. With the debate raging, NASA and its international partners marshaled their most powerful instruments. This wasn't a casual glance, it was a coordinated, multi-platform investigation led by Tom Statler, NASA's lead scientist for small bodies. The agency dedicated priority time on the James Webb Space Telescope, using its near-infrared spectrograph or NIR-SPEC, to perform detailed chemical analysis of the gases in its coma. Simultaneously, the Hubble Space Telescope's Wide Field Camera 3 was used for high-resolution imaging to search for any faint dust or fragmentation events with its superior resolving power in visible and ultraviolet light. On the ground, a network of observatories, including the twin 10-meter mirrors of the Keck Observatory in Hawaii, began a long-term monitoring campaign to track its brightness and trajectory with pinpoint accuracy. The goal was to leave no stone unturned, to precisely measure its path to within a few milliarc seconds, to analyze its chemical composition, and to study its light curve for clues about its shape and rotation. This multi-wavelength, multi-observatory approach is, honestly, the gold standard in modern astronomy for characterizing a novel object. Comet behavior confirmed. So what did this powerful array of telescopes actually see? The answer was unambiguous and came sooner than many expected. As 3I Atlas drew closer to the Sun, crossing the orbital distance of Jupiter at approximately 5.2 astronomical units, which is about 483 million miles, the solar radiation began to warm its icy surface. Just as predicted by standard cometary models, it started to sublimate, behaving exactly like a comet. Astronomers watched as it developed a distinct coma, the fuzzy, gaseous atmosphere around its nucleus, which grew to over 50,000 kilometers in diameter. Shortly after, a classic tale of gas and dust began to form. Tom Statler summarized the findings. It looks like a comet. It does comet things, and the evidence overwhelmingly points to it being a comet. The observation of outgassing with a dust production rate estimated at over 50 kilograms per second provided the natural explanation for any minor deviations in its path, rendering the artificiality hypothesis unnecessary. This behavior began right around the frost line where water ice turns to gas, a telltale sign of a natural cometary body. Chemical composition analysis. But confirming it was a comet was just the beginning. The real prize was in its chemistry. A team led by Dr. Anjali Sharma, a planetary scientist at NASA's Goddard Space Flight Center, used the James Webb Space Telescope's spectrographs to break down the faint light from the coma into its chemical fingerprints. The analysis revealed familiar substances like water ice and carbon dioxide, but with a major surprise. 3I Atlas had an unusually high ratio of carbon dioxide to water, measured at nearly 35%. This vital clue suggested the comet must have formed in an extremely cold region of its home star system, far out in its protoplanetary disk, where CO2 could freeze out in large quantities. Furthermore, analysis of the dust grains showed a polarization signature with negative branching at a phase angle of 22 degrees, suggesting a surface composed of very fine, porous, fluffy dust grains, a sign of a very pristine, unaltered body. This fluffiness implies the grains have not been heavily processed by heat or collisions, making them a near-perfect sample of their native environment. This chemical snapshot provides invaluable data for models of planetary formation in other star systems. Trajectory and safety assessment. With the "what is it" question settled, NASA also moved to definitively address any public concern about its path. The coordinated tracking campaign from both space and ground-based telescopes allowed for an extremely precise calculation of its orbit. The agency confirmed that 3I Atlas posed absolutely no threat to Earth. Its closest approach to our planet will be a very safe 1.8 astronomical units, which is about 273 million kilometers or 170 million miles away. Its perihelion, or closest approach to the Sun, is predicted for January 12, 2026, at a distance of 1.5 AU, placing it between the orbits of Earth and Mars. NASA's Planetary Defense Coordination Office used this as a perfect real-world test of their tracking systems, proving they can accurately predict the path of even novel interstellar objects with incredible precision. After it loops around the Sun, its hyperbolic trajectory will ensure it is flung back out into interstellar space, never to return. Its brief passage is a fleeting but precious scientific opportunity. Natural anomalies in cometary physics. The whole 3I Atlas controversy really boils down to a single fundamental question in science. Is an anomaly evidence of something artificial, or is it a sign of a natural process we haven't encountered before? Science almost always bets on the latter. Our own solar system is filled with comets that behave in bizarre ways. Take Comet 29 P. Schwarzmann-Wachmann, which can increase in brightness by over 15 magnitudes, a factor of 1,000,000, in just a few hours due to cryovolcanic eruptions. Another example was Comet C 2019 Y4 or Atlas, a different comet which unexpectedly disintegrated into multiple pieces as it approached the Sun, showing how fragile these icy bodies can be. The point NASA scientists made is that unusual traits are not automatic evidence of engineering. They are part of the normal, messy, and fascinating physics of icy bodies. These anomalies are not problems for science. They are the very data points that lead to new discoveries about how objects form and evolve. Thus, the unique chemistry of 3I Atlas isn't a paradox, it's a clue. Scientific value of interstellar visitors. So if 3I Atlas is not alien technology, why is it so important? Because interstellar comets are windows into other worlds. Each one is a preserved time capsule carrying the precise chemical and physical fingerprints of the environment where it formed. For 3I Atlas, the dominance of CO2 in its trajectory suggests it could be over 7 billion years old, originating from the Milky Way's thick disk, a population of ancient stars that existed long before our Sun was born. By studying its isotopic ratios like the deuterium to hydrogen ratio in its water, scientists can get direct clues about the water in other primordial solar systems, a key factor in assessing the potential for life elsewhere. This is more than a curiosity. It is a preserved fragment of another planetary nursery. Future missions, like the ESA's Comet Interceptor, are being designed specifically to launch and wait in space, ready to chase down the next interstellar visitor for an even closer look. These objects represent a fundamental shift from studying other solar systems through the faint light of their stars to analyzing actual physical samples. Comparing three interstellar objects. To truly appreciate 3I Atlas, you have to place it in context with its predecessors. The first, Oumuamua, discovered in 2017 with an eccentricity of 1.2, was a complete enigma. It was small, rocky-looking, showed no visible coma, yet had a mysterious acceleration. The second, 2I Borisov, found in 2019 with a high eccentricity of 3.37, was almost the opposite. Its nucleus was about 1 kilometer wide, and it behaved like a classic comet, allowing for detailed study. 3I Atlas, with its eccentricity of 1.8, falls between these extremes. It behaves like a comet, which sets it apart from Oumuamua, but its distinctive chemical ratios make it stand out from a standard comet like Borisov. This growing diversity is forcing astronomers to create a new classification system for interstellar objects. The current rate of discovery suggests that at any given time, there are likely thousands of interstellar objects within our solar system, but most are too small and faint to detect. As our technology improves, we can expect to find many more of these cosmic messengers, each one adding another piece to the vast puzzle of our galaxy. In the end, Comet 3. I-Atlas isn't alien technology, it's a natural interstellar comet, a stunningly beautiful and scientifically priceless messenger from another star system, shedding gas and dust as it speeds through our cosmic neighborhood. The real story here isn't science fiction, but the incredible power of science itself to solve mysteries and reveal the universe's secrets. It's a rare glimpse of pristine material from another world, reminding us that the cosmos is far more diverse and fascinating than we can imagine. For more deep dives into the mysteries of our universe, don't forget to like, subscribe, and hit the bell icon. The universe always has another surprise waiting. Thank you for watching InnoVision Tech.